Hi, good morning everyone. We are Team Uncommon Emitter and we are here to propose our project, which is the injury prediction using human motion capture and tracking of athletes. According to our research, athletes often face injury from various factors such as excessive training load or improper gait posture. All of these injury factors can be identified and prevented in the early stage to keep the athlete healthy and safe. Therefore, there are several identified problems will be solved in this project. First, current methods of injury detection rely heavily on subjective assessment and lack of accurate feedback tool for purpose. Therefore, there are several identified problems to be solved in this project. First, current methods of injury detection rely heavily on subjective assessment and lack of accurate feedback tool for performance tracking. Next, the existing motion capture system rely on high cost marker based system which makes the injury prediction in early stage challenging. The aim and objective of this project is to develop an AI-based software that can analyze athlete performance and predict injury in the early stage through machine learning models. So, our system functionalities revolves around using optical flow-based motion tracking and active sensors to capture detailed biomechanical metrics. These metrics will be used for gait analysis and injury prediction through machine learning model. For the methodology, our system uses optical flow-based motion tracking for gait analysis and sensor-based strike and speed measurement to collect training patterns. Next, the learning model will be trained with training data for injury prediction. Lastly, all of these functions will be integrated into an user-friendly GUI. Hi, I'm Ming Jun, and I will be presenting my part, which is the optical flow-based motion tracking and gait analysis. The design process can be categorized into two parts. First part is the open pose motion tracking model that is trained with MPI human pose and Coco key points. The model will receive the training footage as input and provide output video annotated with key points. The body key points will be saved in JSON file for gait analysis. The next part is a gait analysis model from Stanford, which is trained with improper gait and injury posture datasets. The model will pre-process the key points from open pose and input into the model to get different biomechanical gait metrics. This is the final result of my part, which shows the motion tracking output video and the gait parameters analysis. The analysis will show overall gait deviation index, gross motor function classification system, speed, cadence, and the maximum knee flexion of the athlete. However, there is still some limitation in my system. First, the motion tracking and gait analysis model requires strong GPU, so lightweight models can be implemented to improve the speed of real-time analysis. Next, the gait analysis model is a generic model for running only. Therefore, it can be enhanced by developing more customized models for specific sports. That's all for my part, and I will pass it to the next person.
My name is Lijan Tom, and the part that I worked on is training the injury prediction model using machine learning. These are the features that the model was trained on. There are 10 of them. The green ones indicate that they are obtainable from our sensors, while the red ones require manual input. The speed of running are separated into three parts, from slow to fast, which are sprint distance, zone 3 and 4, and then zone 5, track 1, and track 2. The dataset that I used to train the model are structured to allow the model to recognize patterns of data in the previous 7 days before the injury occurs. For each day, the data will have 10 features, which are the ones that I mentioned in the last slide. So for 7 days, the model will require an input of 70 features. The graph on the left shows how well the predicted probabilities align with the actual outcomes, where a perfectly calibrated model predictions should fall along the diagonal dotted line. The graph on the right shows Zone 5, Track 1, and Track 2 sessions on the day before the injury play the most important role in deciding an injury might occur or not. So let me show you how the model works. So this is the code, and then when I run it, so let's go to the data set and select a random row of data. Let's select this one. So I copy the whole row and then I paste it in. So as you can see, the combined predicted probability is 0.677, which means 67% of an injury might occur. So in reality, all these numbers will be obtained through the program.
Hi, I'm Sang Chin. Today, I'm excited to share a system I developed that monitors your steps and running speed in real time. The system includes two key parts, a wearable sensor with a gyroscope LSM6DS3 and a data receiver, which can be a computer or a smartphone that runs Python and connects to Wi-Fi. The gyroscope is tiny, just 1.5 cm wide. It converts physical motion into digital data, and ESP32 processes this data and calculates the number of steps and speed, and sends this information to a device via Wi-Fi. Here's how to use it. First, attach the sensor to your leg. Make sure both the sensor and your device are on the same Wi-Fi network, and that the device IP addresses is entered in the code. When you start the system, the ESP32's LED will blink as it connects to Wi-Fi. Once connected, the LED will stay lit, showing it is ready to use. I will now demonstrate. Notice the LED on the ESP32 is on, indicating it's ready. As I move, the sensor tracks each step, swing range, and speed, sending this data instantly to my computer. This speed data can be used by a deep learning model for injury prediction, helping me analyze and adjust my running. Thank you for your time. Have a great day.
This is the GUI of the group component. So I will select a video input. This I will demonstrate the human motion capture and tracking of athletes using vision-based injury prediction designed by Mingjun. So right now I input a video and then I run motion tracking to run the algorithm. As you can see at the command line interface, the code is running at the backend. And now the analysis result is shown. So when I press the play video, the annotated video will come up using Mingjun's models. Now I will close the window. To close the window, I will terminate the process. And for part 2 of the vision-based injury prediction, there's a run real-time tracking function which I will demo right now. For some reason it's not working, so I'll proceed to the next function, which is using training data, which using a CSV file as an input. And after inputting the file, you can use to start prediction. Now I will record the training data, as detailed steps will be explained earlier by Jantom. So I will demonstrate how to use the GUI to navigate through the process. So when you enter the zones and then pressing start collecting data, it will show the simulate speed. After you clicking the stop collecting data, then you need to enter a number of parameters described by Jantom earlier. Then you click submit to submit the data to the program. Now the data is successfully recorded. Now I will try another data set. Now I enter the parameters. That's all for my GUI